Only one company on the entire planet builds the machines that print the world's most advanced computer chips. That company is ASML, based in a quiet Dutch town. Its power comes from a single part that almost nobody can name. Not the scanner itself, the light. Then, a team of physicists connected to Tsinghua University published work in Nature showing a completely different way to create that same light. A method that skips ASML's process entirely. It is the one thing this monopoly was never designed to handle. Making that light is so difficult that for decades many scientists called it impossible. ASML solved it by blasting 50,000 tiny drops of liquid tin every second with lasers hotter than the surface of the sun. That solution took roughly 30 years and tens of billions of dollars. Now researchers say you can get the same light by sending electrons around a giant ring instead. No explosions, no metal debris, just a steady beam. If you like videos that go deep on stories like this, it takes a lot of work to put them together. Please hit the like button and subscribe so you do not miss the next one. What comes next involves a physics idea that sat largely ignored for about 10 years, a laboratory in Germany that proved the mechanism is real, and a discovery that quietly opened a second possible road to the most important light in modern technology. The big question is simple. What if the hardest part of making chips was never the machine itself, but the light? And what if nobody was fully guarding the second path to that light? In February of 2021, a team of physicists published a paper in Nature, one of the toughest science journals in the world. They had taken a theory that had been sitting on the shelf for more than a decade and showed that the basic mechanism actually works. The idea is called steady-state microbunching, or SSMB. It points to a different way to generate the extreme ultraviolet light that prints the most advanced chips, without relying on the tin plasma process that ASML uses. The core concept came from an American physicist named Alexander Chow, one of the most respected accelerator scientists alive. He and his student Daniel Ratner at Stanford developed the theory around 2010. They published the idea, and then not much happened because no one had the right machine to test it properly. What changed is that researchers, including a young physicist connected to Tsinghua University, pushed the mathematics further. Chow helped connect the group with physicists in Germany. Together with Germany's National Metrology Institute and the Helmholtz Center in Berlin, they gained access to a special machine called the Metrology Light Source. It was the first ring designed in a way that allowed the exact conditions SSMB needs. Here's the part many people miss. The key experiment did not take place in China. It took place in Berlin. The team proved the mechanism works. They did not build a chip factory, but they turned SSMB from a promising equation into something the semiconductor world suddenly had to take seriously. Later papers in 2024 continued to confirm the theoretical foundations and showed further experimental progress, including multi-turn behavior and improved laser systems. Designs for a future kilowatt-class EUV source based on this approach continue at Tsinghua's and collaborating institutes. The work is still research, not production. Yet the proof that the physics is real changed the conversation. To understand why this matters, you first need to understand what ASML actually built, and why almost everyone assumed there was no other practical way. Every advanced chip starts the same basic way. You shine light through a stencil onto a silicon wafer, a bit like shining a flashlight through a cutout to make a shape on the wall. The shorter the wavelength of the light, the smaller the features you can carve. The most advanced chips need light at 13.5 nanometers. That is called extreme ultraviolet, or EUV. The catch is that light this short basically does not exist in any usable form on Earth. You cannot buy an EUV bulb. You have to create the light from scratch. And that turned out to be one of the hardest engineering problems humans have ever solved. ASML's approach works like this. A machine shoots molten drops of tin, each about 25 microns wide, smaller than a grain of sand. The drops fall through a vacuum at roughly 70 meters per second. As each drop falls, a powerful laser hits it twice. The first hit flattens it into a pancake. The second hit turns it into a plasma hot enough to reach around 200,000 degrees Celsius, far hotter than the surface of the sun. In that split second, the dying tin gives off a flash of 13.5 nanometer light. Then the process repeats 50,000 times every single second. The laser itself starts as a weak beam and gets amplified more than 10,000 times through multiple stages until it carries tens of kilowatts. All of that just to hit a tiny drop of metal at the perfect moment over and over for months without missing. Back in the 1980s, plenty of smart scientists said EUV was simply impossible. It took the industry about 30 years and enormous investment to prove them wrong. That 30-year head start is the gap everyone else has been chasing. There's also a messy downside. Blowing up 50,000 tin drops every second inside a sealed chamber creates a lot of debris. Tin vapor and particles coat everything. The system has to pump in hydrogen gas to clean it. The mirrors still wear down, and the whole machine needs constant, expensive maintenance. Every hour spent being fixed is an hour a tool worth hundreds of millions of dollars sits idle. That tin plasma system is the beating heart of every EUV machine on the planet. It is the real reason ASML has no direct competition. The lasers come from Trumpf in Germany. The mirrors come from Zeiss, also German, and they are among the flattest surfaces ever manufactured. The plasma technology traces back to a California company called Cymer that ASML acquired. What ASML truly owns is the know-how to make all these nearly impossible pieces work together, thousands of times a second, for thousands of hours without failing. Decades of knowledge locked inside one company, protected by patents and export rules that gave them power unlike almost anything else in the modern industrial world. ASML is the only maker of EUV chip printing machines on Earth. There's no second supplier. A standard low NA machine costs over $200 million. The newest high-NA models with bigger optics run around $380 to $400 million each. That is for one tool. To make a single cutting-edge chip, whether it goes in your phone or powers artificial intelligence systems, the critical patterns have to be printed by an ASML machine. There is no other door. That position has pushed ASML's market value past $670 billion at times, a European record. One analyst put it simply, the company has the market completely cornered. So that is the board. One company. One extremely difficult light source. An entire world of advanced technology bottlenecked through a factory in the Netherlands. Right now, every leading-edge chip that comes out of a top fab has a piece of that expensive machine cost baked into its price, plus the downtime from tin cleanup and maintenance. The whole industry runs on scarcity. A limited number of tools, all from one supplier, handed out to the few companies that can afford them and wait in line. TSMC, Samsung, Intel. These are essentially the only buyers on Earth who can write that check. When one company controls the single most important tool in the most important manufacturing industry on the planet, that is not just a business advantage. That is leverage on a global scale. Entire nations have to deal with ASML, which means dealing with the Netherlands, which in practice means dealing with the export rules influenced by the United States. And that is why the Nature paper and the continuing SSMB research matter so much. The whole strategy of using export controls to slow certain countries rests on one assumption. The light source is so hard to build that nobody can recreate it and nobody can go around it. Block the machine and you block the most advanced chips. That was the core of the plan. Those controls guard one specific path, ASML's tin plasma machine. They were never designed for the possibility that physics offers a second road to the exact same light. If anyone can make 13.5 nanometer light from an electron storage ring instead of tin plasma, the controls suddenly aim at the wrong target. They guard one door while someone cuts a new opening through the wall 100 meters away. That is what a monopoly fears most. Not a copycat playing the same game a little worse, but someone who refuses to play that game at all. A monopoly on a road only lasts as long as the road is the only one. To understand what the Tsinghua-linked team and their collaborators are chasing, forget tin drops entirely. Think instead about a ring, a racetrack for electrons called a storage ring. It is the kind of particle accelerator you usually find at a national physics laboratory. You take a beam of electrons, speed them up to nearly the speed of light, and send them looping around the ring again and again. Normally, the electrons in that beam are spread out in relatively long, loose clumps. Those loose clumps give off ordinary light that is useful for science, but nowhere near strong or focused enough to print chips. The trick being developed squeezes those loose clumps into something special. Using a carefully tuned laser inside a device called an undulator, the electrons are nudged so that after one full lap around the ring, they snap into tiny, evenly spaced microbunches, each only about a micrometer long. When electrons are packed that tightly and that evenly, something remarkable happens. They stop radiating like a regular bulb and start radiating more like a laser. Their light waves line up. Because the electrons keep circling, they keep doing it without stopping, in a steady state. That is the whole idea behind the name steady-state microbunching. Now, compare that to ASML, because the contrast is the entire point. ASML's source is essentially a strobe light. It makes EUV in 50,000 separate explosions per second, with all the tin debris and downtime that brings. The SSMB approach blows up nothing. No tin, no drops, no debris to clean. Just electrons in a ring coaxed into producing a smooth, steady, laser-like stream of EUV light. On paper, the research describes a path toward kilowatt-level average power in the EUV range. For context, current ASML sources deliver a few hundred watts at the source. The company is pushing hard towards 600 watts and eventually 1,000 watts or more. SSMB aims at similar or higher power levels from a completely different starting point. Raw power matters enormously. EUV light is so easily absorbed that you cannot focus it with normal lenses. It is absorbed by glass and even by air. The entire light path inside these machines uses mirrors. Even the best mirrors lose roughly 30% of the light with each bounce. The light may bounce around 11 times on its way to the wafer. After 11 reflections, only a tiny fraction of the original light reaches the silicon. You have to start with a huge amount of power just to end up with barely enough. That is the wall the tin plasma strobe keeps hitting. A steady, laser-like source is one possible way to push through it. Here is the part that should grab attention. A single one of these rings would not necessarily feed only one machine. Because the electrons circle a large loop, you could place multiple printing stations around the outside of the ring, like desks arranged around a central light source, and power several of them from the same accelerator. One giant light source potentially serving an entire floor of a chip factory. In some Chinese discussions, this idea has been nicknamed the lithographic cannon. That flips the economics in a way that is easy to miss. ASML's model is one big, complex light source bolted to one scanner, sold for hundreds of millions of dollars, one at a time. A storage ring approach changes that. You build the hard, costly part once, the accelerator, and then attach simpler printing stations to it, as many as the ring can support. If that ever works at production scale, the most expensive piece gets shared across many machines instead of being loaded onto each one. The current pricing model starts to look different. Think about what a stronger, cleaner, potentially shared light source would do to the industry. Right now, the scarcity of EUV machines is part of what makes them so valuable. Only a limited number exist, all from one supplier. That scarcity is baked into the price of every advanced chip. Open up the light source and you threaten the scarcity itself, which is the exact thing that supports ASML's enormous valuation. Some analysts now talk about a future where chip making could split into different technical tracks. A Western track built around ASML's EUV tools, and other tracks that explore accelerator-based sources. Whether that full split ever happens, the fact that it is even being discussed is a change. For roughly 20 years, there was essentially one practical path to a cutting-edge chip. That is no longer as certain. Leverage is the word that matters most. For years, export controls worked partly because everyone believed the technical wall was airtight. There was no realistic way around ASML. The moment a credible alternative appears on the horizon, even one that is still years away, that belief begins to crack. SSMB does not have to print a single commercial chip to start changing the strategic conversation. That is also why significant investment continues to flow into alternative approaches. China has put substantial resources into building domestic lithography capabilities from the light source upward. SSMB is one of the longer-term scientific bets in that effort. There is also interest in other plasma methods, though those remain less proven. The larger point is the ambition. The goal is not simply to copy ASML's machine a little worse. It is to explore a different branch of physics that could make catching up on the original path less relevant. You can block a company from buying a specific machine. It is much harder to block an entire country from pursuing an openly published scientific idea, especially when the core theory has been in the literature for more than a decade. Now comes the cold water, because it is important. The 2021 experiment and the follow-up work proved the mechanism. They did not build a working chip factory. The gap between those two things is enormous. Anyone claiming this monopoly is already broken is overselling the story. In the early tests, the electron bunches carried only a small fraction of the charge a real industrial source would need. Going from a laboratory demonstration to a machine that prints millions of chips with almost no defects is a completely different mountain. Remember that ASML's own path from impossible to working production tools took about 30 years. China and others are essentially starting that clock now on just the light source. And the light source is only one part of a machine that contains hundreds of thousands of precision components. Researchers at European chip research centers point to what they call the yield gap. That is the brutal distance between making nice light in a laboratory and printing millions of chips where almost none are defective. You can have the strongest, cleanest EUV beam ever made and still fail if your mirrors are a tiny bit off or your chemistry is not perfect. That is the part money cannot fully accelerate. It takes time, repeated failure, and years of hard learning that cannot simply be downloaded. There is also a practical reason this has not happened yet, and it is not because Western engineers were asleep. Building a storage ring is a massive undertaking. Plans discussed for an SSMB facility talk about a ring on the order of 100 to 150 meters in circumference. That is a national-scale infrastructure project, not something you assemble on a normal factory line. And the physics still has open questions. Getting from the Berlin demonstration to a stable kilowatt-class EUV source that runs reliably all day inside a production environment is years of hard work at minimum, and it could still hit obstacles that have not yet appeared. None of that means ASML can simply relax. China is not the only one paying attention. In the United States, a startup called X-Light is pursuing a related idea using a free electron laser driven by a particle accelerator to generate EUV light and potentially feed multiple existing scanners. Other groups are exploring compact accelerator concepts as well. Serious money and serious physicists on both sides of the Pacific have reached similar conclusions at roughly the same time. The tin drop strobe, as remarkable as it is, might not be the final answer for all time. The future of the most important light in the technology world might eventually include particle accelerators. The moment that stops being a distant maybe and becomes a concrete when, decades of advantage in tin plasma technology stop being an unbreakable wall. They become a very impressive head start in a race that suddenly has more than one lane. ASML's own teams continue to talk about pushing their tin plasma design toward 1,000 watts and beyond. That confidence is earned, but it is the confidence of the incumbent, the company betting that the current method will remain dominant. History is full of incumbents who were excellent at what they did right up until somebody else did something completely different. What the team showed in Berlin and what the continuing research is refining does not break ASML's monopoly today. It may not do so for a decade or more. But it proves something almost as important. It proves the monopoly was never permanent by the laws of physics. ASML's edge has always rested on owning a single critical bottleneck. A monopoly on a bottleneck only lasts as long as the bottleneck itself remains the only practical path. If you like this story and want more like it, hit the like button, subscribe, and turn on notifications so you never miss the next one. There are related videos on the screen right now if you want to keep watching. Here's a question for you. If you were running ASML, would you invest in building your own accelerator-based light source? Or would you double down even harder on the tin drop method and push it further than ever? Let me know in the comments.